So it's a great pleasure to be here. It's my second time at IBA. Last time I just stayed at the guest house, but now I have a chance to enjoy full campus. And it's good to be given a chance to give some lectures on what I work on to some enthusiastic people. Normally, I would have done a talk using the whiteboard, but that takes even more time to prepare. So I'm sorry to say I made slides, and I'm even sorrier to say I'm using PowerPoint, because anybody who was in my group knows that I don't like using PowerPoint. But forgive me, I prepared some PowerPoint slides, and so this is how I'm going to discuss. Gibran asked me to give a talk on kind of applied quantum algorithms leading up to machine learning, which I'll do. I haven't given these lectures before, so you're my test case where I'll go through and discuss various issues. I'll start off with basics today. This afternoon, I'll lead more into that. I'll get an idea of what you want to hear about. And then by tomorrow's final lecture, I'll make sure that I cover where the quantum machine learning is going. All right, so I just called it using quantum computers. Most of my work is on what I call building a quantum computer, the hardware side, but I do quite a bit of quantum algorithm stuff. And so I give talks on building quantum computers, so this is kind of going to be the flip side if I give more of these lectures on how to use them. Okay, now I got to figure out this. Okay, so I know you've covered some of the basics on computation. I went through the slides from the Rigetti talk. How many people here do computer science? Oh, quite a few. Okay, good. And physics? Fewer. Okay. So that's fine. I'm a physicist myself. I like it. But knowing there's a lot of computer scientists here is good, because that's the way I want to pitch things. But I'll give some basics on computing too. The other thing is I'm going to give basics of computing, but it's my own simplified perspective. So I'll be describing things not in a standard textbook kind of way. And so just to begin with, I'll tell you what, I'm going to give you my definition of a computer, and anybody can correct me if you want. Essentially, to me, a computer is just a machine that is designed to do computation, to solve problems. I put in brackets here whether it's universal and programmable. In what we do with quantum computing, some of the work is done to make a universal quantum computer. The Rigetti computer that you heard about is of that type. Other computers are specific to solve a particular problem. It gets a little bit muddy with, like for example, D-wave adiabatic quantum computing or quantum annealing, because it's a specific hardware type, but then they can program to set the parameters of the machine. Okay, a computer simply to me accepts as input information, which is in bits, and then it yields as output information, which is in the form of bits. So to me, a computer is just a machine where bits go in and bits come out. And the bits go in, they formulate the question and possibly the program. And the output, the bits, are just the answer to the problem. And inside the machine, we have a sequence of instructions. And the instructions are hardware specific. So most of what we would learn in computer science is really tied to a specific kind of hardware. We use transistors, for example, and different kinds of memory to store and process. And then much of what we do in computing is based on hardware instructions that are based on Boolean logic and natural to Boolean type gates, and or not, XORs, NAND, and so on. And so the idea is that we have to somehow boil down the computation. There's a computational problem. There's an algorithm to solve it, and then we have to boil it down into a set of specific hardware instructions. What makes the quantum computer special then is that inside the machine, we're using quantum mechanics. So to me, the input is still bits, the output is bits, but the hardware is quantum mechanical in nature, and that's what we exploit to advantages. So the applications that we look for in various fields are applications that build up on that. And I'll explain a little bit about it, but I don't want to go much into the hardware. I will point out that this is not a universal definition of quantum computing, and I'll touch on this when I get into the quantum simulation type algorithms. So the quantum simulation would be best described by quantum input, quantum output processing. I'm not so fond of that. I always think that the quantum simulation has to be couched in a proper computational problem. So although you'll read a lot of papers if you go in that direction on quantum simulation, just bear in mind that my point is these things are only useful if in the end we have a classical information in, classical information out. Okay, so that's what the computer is, and then we have computation. And so there's actually computing and computation, they're different words. Computing is what the computer does. Computation is the physical process in the machine. We have a problem, we formulate an algorithm, then we tell the machine how to execute the algorithm. And I know again in the Rigetti slides that I looked through, they were teaching you PyQuil, right? So you have PyQuil, and PyQuil, they construct a programming language, and the idea is simply you know what the algorithm is, then you formulate it in your programming language, it goes through the architectural stack down below and eventually tells you how to execute on the machine. And so computation to me is just the physical process on the machine. It's determined by the algorithm, and it's specific that you need a well-posed problem. And making a well-posed problem itself can be a bit of a challenge. There are different kinds of problems that we want to solve. And I put a few down here. The decision problem, where the answer is one bit, so it's yes or no. There are function problems, like find the sign of x. A search problem, commonly we might talk about a database. So given some element, find the input. It's also a function inversion problem. See if you can see it. So given f, and f carries x to y. Is that visible to everybody? So I know for later, okay. So then given y, find the value of x. So that's a function inversion problem. Promise problems, where you're promised that certain cases don't occur. And then these come up. Decision problems, I'll explain more. Decision problems are used typically to assess complexity, and other problems can be cast as decision problems. Function problems, common. Search problems, you did Grover's search in the class, so Grover's search is of that type. The promise problem, you've already done Deutsch-Jose here, right? That was in these lectures. So Deutsch-Jose's, where the function is promised to be balanced or constant, that's a promise type. Optimization is a very important aspect of science in many, many areas. It's really find the maximum or find the minimum, find the best solution. There's another variant known as the feasibility problem, where instead of looking for the best solution, it's to look for a good enough. And there are many more cases. So often we need to think about all these types, but we can reduce them often to just decision problems. So from a theoretical point of view, we can study this type and then extrapolate to do other kinds of problems. Okay, so let me just go through the decision problems. By the way, if you have any questions, feel free to interrupt anytime. Okay, so decision problems is how we'll focus on understanding the nature of computation and the nature of the computation and complexity and so on. So I'll just go through this. Apologies if you already have a strong background in this, but I won't dwell on it for a long time. So the decision problem, as I said before, maps to a single bit. So mathematically, I could just consider the function, and the function will take a string of bits. So 0 and 1 are bit. 0 and 1 is a bit. The star superscript means it's a string. If I put a letter n, it would be an n-bit string. Star means it's arbitrarily length. So it maps a bit string into a single bit. And it could be yes, no, true, false, so on. Okay, so it's just, that's the idea. That's a Boolean function. So the decision problems turn into Boolean functions. Once we recognize that, we're able to then take the Boolean function and decompose it. So one important aspect of computation is that the program in a decision problem is simply a Boolean function. And a Boolean function can be simplified to just very simple Boolean gates, Boolean logic gates. And in fact, it can be decomposed into only NAND gates. And I wrote the NAND gate here. This is the standard ISO standard circuit description. It's the not and. So it accepts a single bit A and a single bit B. And the not and then puts out not of the product of A, B, which I also wrote here in another way, the not of the product. And you can see the truth table over here. Okay, so you do the and of A and B, and then you take the not to get the output. It turns out that that's the only gate that you require to construct any Boolean function. I kind of like that because when I dabble and try to work out complexity of things, complexities of functions, then I'll write a circuit. I'll only use NAND gates. So at every step, there's either a NAND or an identity. And then I can look for the time cost as the longest path through the shortest circuit. And I just count the number of NAND operations. So for me, it's very convenient. There are other ways, of course. There are many, probably infinite ways to decompose. But, and it doesn't matter. The way that we deal with complexity, we don't care about the specifics of which gate you use and exactly what circuit. We care about how the number of gates grows with the size of the problem. So given a problem of some type, is 17 a factor, and then we grow the number we're checking, we keep growing it, we can look at how the number of NAND gates scale with the size of the number that we have to have as input to solve, and then we look at that kind of scaling. Pardon me? Okay, thanks. Oh, I think you flipped the slide. Thanks. Yeah. Okay. Red. 10% of people are red-green colorblind. So 10% of the class, yeah? So I was aware 10% can't see that red dot. All right. Okay, so anybody who's red-green colorblind, just let me know if you can't see what, if you want to. Okay, so yeah, that's the Boolean function. We could decompose into NAND gates, and then ultimately the question is, how does the cost scale with the number of NAND gates? That's the complexity. And the whole point of quantum computing up until the last few years has been to identify computational problems for which the complexity using a quantum computer scales better. Now, when I say better, in Grover's search, the idea is that the cost goes down quadratically. So if you need n gates to solve the problem, it would scale as square root of n. In the case of factorization, it's sub-exponential. So there's a sub-exponential, so it's almost exponential cost to factorize numbers. Is that me? No, somebody's phone. Okay, so there's the number of gates will go almost exponentially with the size of the problem, and then with Shor's algorithm, it will grow polynomially. So we need to understand the concept of complexity to understand what the advantage is for the quantum computer. These are often expressed in terms of worst case. So you take a problem, and then you want to know what is the complexity of solving the worst case problem. I'm just mentioning that carefully because like tomorrow I'll get into quantum machine learning stuff. And there's a lot of conjectures that aren't proven. So the idea is that there's a hope that quantum computing will accelerate those problems. And theoretically, we don't know one way or the other. And part of the issue is that they're often of the optimization type that we need to deal with. Also, there could be linear equation solvers. And those ones, we might just care about typical case. So in the theoretical computer science, you prove worst case results. And in the real world, they often want typical case results. So it's hard to make very strong statements. Okay. So this is the idea. That's what the complexity is. Any questions about that slide before I go on? I can always come back to it. Okay, so this I took this picture to kind of give you an idea of the complexity diagram. This hasn't been covered in the lectures, right?
Some of these classes have.
Oh, you've done. Yeah. Oh, P-space you've done. Not all these though, right?
Pretty much everyone.
Yeah, you've done all of them. Okay, then I can go through it quickly. Okay.
But not this way.
No, yeah, no, I grabbed this picture.
Yes. It's giving a complete picture.
Yeah, I took this, I feel badly, I should have put all the references. This was off the MIT open courseware site. So I just grabbed their picture this time. I usually use a different one, but then I was looking last night, I like the MIT one. And then this is done by Scott Aronson, back when he was at MIT. And so we have our space cost, time cost, and I'll go quickly through it, but I'll just remind you. And then the problem complexity deals with how space and time costs grow. Time cost, I like to think about classically, again, in terms of the number of Nand gates and the longest path through the shortest circuit to solve the problem. And it's always looking at how it grows with respect to the number of bits required to specify the problem. And then the nice thing about this picture is that it mentions p-space, but then it gives examples. In this case, it mentions chess and Go. I don't know if you know Go. Go is the Japanese name of a game with 19 by 19 lines and stones put on it. So they both live in p-space. P-space would be the set of problems where a number s grows polynomially with the size of the problem, but the time can grow exponentially. And then there's other ones here. P polynomial class. So these are problems that can be solved in polynomial time. BQP bounded error time, quantum polynomial time, bounded error quantum polynomial time. These are the ones, these could be solved efficiently on a classical computer. These can be solved probabilistically in polynomial time. So most of the time, let's say 2/3, it will give the correct answer on the quantum computer. And this is important because this is where factoring and discrete logarithm work. So they would be non-deterministic polynomial time. They would be easily verified, efficiently verified, but take, say, exponential time to solve. And this is eating up some of those. The transfer of some problems from here to here is what certainly 25 years ago, when Shor's algorithm came out, justified a lot of the excitement in quantum computing. That these problems, factoring, discrete logarithm, and others of those type, are the reason that we trust our internet security is because we think that an adversary, by establishing a long enough key, we can stop an adversary from having the computational power to break our codes, like RSA algorithm, elliptic curves, those things. So the idea that a quantum computer makes these kinds of problems easy to solve justified a lot of the excitement that has gone on in the last quarter century. That a quantum computer is a threat. It threatens the security associated with encryption to protect the internet. I hope that's clear. This is, I would say more, but you've covered this, I guess, so I'm not going to go into it.
But a clarification of the picture should be right, that this is not all proven. That the picture is actually more an intuition of what we expect is true.
Yeah, okay. Yeah, so what Gibran's saying is correct. I'll add, he's reminding me to be very careful that these are all assumptions, conjectures based on beliefs that things don't collapse. A lot of these things could collapse into one. Can't prove otherwise. So yeah, there's always a caveat put on these to say, this is hard as long as BPP is not P, or as long as NP is not P. So that's right. These are conjectures, and there's very few lower bound proofs. Yeah, thanks for that point. Okay. Yeah, and then there's a set of problems here that live in P. You can see these lines. P and BQP are efficiently solved by a quantum computer, and so on. Okay, so that's just a quick rundown of computational complexity theory. Okay, I want to throw this one in. I'm just going to tell you that, so just going to give you my own intuition on quantum computing. It turns out it's not generally in the textbooks, but the idea is that there's kind of there was a historical and logical step that took place going from computing in the sense of Boolean logic to quantum computing. And so I like to throw this in because it certainly helps me understand, and I'm just going to explain it here. So it's the idea of reversible computing. For physicists, you would know that there's Maxwell's demon, famous problem. And Maxwell's demon led to the concept that entropy is negative information. Okay, but the computer scientists don't need to worry about that. The idea that evolved out of a physics problem explored for 100 years became a big deal at IBM back in the 1960s. And so the idea is that computer chip sizes are limited by heat generation. So, you know, we would like to be able to, this is not quantum computing, just classical computing, but right now chips, as you know, are just two-dimensional. And why can't we do three-dimensional chips? It would really be a great advantage. Why can't we pack more on a chip? And so one of the great problems, especially in going to 3D chips, is the heat generation. Got to get rid of that heat. Got to bring wires in, they create heat. And so one of the theoretical questions came up is, why do we have heat in the first place? And in Boolean logic, what happens is we have, like if we take that Nand gate here, we put 2 bits in, we get 1 bit out. That means we have to throw something away. The cost of throwing something away, that erasure, as pointed out by Rolf Landauer at IBM back in the early 1960s, incurs a cost. And the cost is kT log 2, which is Boltzmann's constant times the temperature in Kelvin times a constant multiplier. And so every logic operation with erasure generates heat proportional to the temperature of the system. And of course, that raises the temperature of the system. So you generate heat, more heat, more heat, more heat, and that has to be dissipated. It's not practically important yet because the heat cost in this case is about 1,000 times less than the actual cost in current computers. But it's interesting theoretically. So then out of IBM in the 1960s, the idea was to start doing, I didn't put all the details down, but I'll explain. So the idea was to replace Boolean logic by reversible computing. And reversible computing has the property, every mapping is reversible. So it takes a bit string of some length to a bit string of the same length, that every computational step can be reversed. And then the idea of reversing it means there's no erasure and therefore no heat cost. The downside is you have to carry a lot of garbage. So it carries a lot of garbage through the system, but the heat can be dissipated only at the end after the computation. Okay, so then the idea here is that given any Boolean function, this type, so given any Boolean function, there's a way to embed it into reversible computing, and it's kind of trivial. And basically, reversible computing is simply permutations. So you have your bit string, and then you have one, so whatever the problem is in this case, so if you have a Boolean function acting on a bit string of some size into a single bit, then you replace the bit string by the bit string with 1 extra bit. I think it was a scratch bit, something to write on. And then you map it to the same size, and the last bit is the answer, and all the early bits are just carried over. And when you do that, this function capital F is then just a permutation. So you can use the mathematics of permutation and decompose. So remember I pointed out here that every Boolean function can be decomposed only into Nand gates, that type. So when you do that, you embed into reversible computing and do the permutation, then every function here can be reduced into very simple permutations. Whereas in the Boolean case, it's 2 into 1. You can show mathematically that the decomposition here has to be at least 3 into 3. So 2 into 2 is not enough. And down here, some of these gates you'll have seen. So that's the NOT gate, the controlled NOT. Toefl Gate is control NOT. You know this notation? Is it covered? Sorry? Yes, and yeah. Sorry?
I want to understand.
Okay, but yeah, I can explain it. I'm just wondering if that's been done in these lectures. Oh, definitely not. Okay.
The third one is not.
Okay.
It's not been done in the talks in detail, but some people know
Yeah, okay. So, but if they haven't done it in the talks. The NOT gate, you know. So you said you could read over here. So this is all classical, not quantum. So even what you did here would have been quantum. But this idea, this is the NOT gate, capital X. So you saw before, I saw in the Rigetti slides, this, right? This kind of thing. But that's not what I'm doing here. So we're not doing, this is really, classically, this NOT gate takes 0 and maps to 1, and it takes 1, maps to 0. But that's just purely classical logical bits. And then what happens here is, you might know, that if we take 0, 0, it goes to 0, 0, because this controls this. So if that's a 0, no NOT operation. If I change it to a 1, it stays the same. But if I make it a 1, 1, 1, correct, and then this will go to 0, and so on. Okay, so that one is clear? Okay, then let's add one more. So then we have, it turns out that if we have 1, 1, and then we take 0 or 1, we get 1, 1, 1 or 0. So the effect, if they're both 1, then they execute the NOT gate. But if either one is a 0, then we don't execute it. Okay, so it says control, control. So only if that's 1 and that's 1 does it execute that gate. Clear? So that's known as the Toefl Gate, and that emerged out of reversible computing. So Toefl and Fredkin were two of the early active people in the 1960s on reversible computing. And then it turns out, so I just did this sequence so you could see how you build up the Toefl gate. Not, control, not, control, control, not. So it's 3 bits in, 3 bits out. And it turns out that this is a reversible equivalent of the Nand Gate. And so this can be decomposed into here. So if you take reversible computing, you embed your Boolean function into reversible computing, you can take a circuit, decompose according to the mathematics of permutations into Toefl gates, it's a permutation. And then, so you decompose in that, you count the number of Toefl gates to do the circuit, and then you discover, importantly, that when you do the embedding and you count the number of Toefl gates, there's no change in complexity. So if something is polynomial time complexity for executing a Boolean circuit, it'll be polynomial time complexity for the reversible computing circuit. So reversible computing it continues to be a nice area, but it's rather esoteric because it delivers no advantage in terms of complexity reduction, but it was to address the problem of heat generation. Unfortunately, it's never turned out to be practical. But that was where IBM was. I'll just tell you, there's the IBM Quantum Experience. So IBM is a big player in superconducting quantum computing. And interestingly enough, IBM has for 50 years wanted superconducting computing. So one of the reasons they're very interested in quantum computing is it takes them back to these roots from the 1960s where they were exploring superconducting computing. They still regard that as a target. Again, the idea is to break the two-dimensional limit to chips. There was another person at the time, Fredkin, and Fredkin had a different gate. I wrote the logic, well, I have the logic operations here. And so in this case, bit goes in, and so this is controlled swap. So if this is 0, these bits go through, and if this is a 1, then these 2 bits swap. And we can always write it in terms of Boolean operations. Same, I didn't put the Toefl ones, but they can always be related to Boolean operations. So given a particular function to evaluate that represents the computer program, then the function can be reduced down to a sequence of it could be reduced down to Fredkin gates, and we could write the circuit in that way. So we could write the circuit in terms of Toefl gates, count those, and then see how that scales. That gives us the complexity. Or we could equally well reduce it down to the Fredkin gate. And by the way, this says Feynman because Feynman's early work in quantum computing, he talked about the C0. So some people even call the C0 the Feynman gate. Okay, so that's the idea. The reason that I highlight it is because conceptually, this way of thinking was important for certain breakthroughs, notably Charlie Bennett. So you'll hear the name Bennett a lot. Bennett and Broussard, 1984, the quantum cryptography protocol. Bennett was the first author of the famous 1993 quantum teleportation paper and various other things. And Bennett emerged from this reversible computing community. And some of the ideas, is anybody going to talk about the recycling that goes on in a quantum algorithm? You know that? No? Okay. So there's kind of recycling steps that are very important. So there was an early objection, early 1960s, Rolf Landauer at IBM objected to reversible computing, and then he objected to quantum computing. Very smart guy, so not putting it down, but he objected saying that these were ridiculous because they incur exponential overhead. And it was Bennett who figured out what he called pebbling at the time. And the idea was that if you prepare things in the right way, then you execute, and then you clean it up or recycle after, you could take exponential overheads down to polynomial overheads. So that kind of thinking that got around naive exponential overheads emerged out of that community. So that's important. Yeah. The overhead is the space and time cost. So what happens is this grows. So your question's good. I'll explain carefully. So we look at how the space and time cost grows with the size of the problem. And so that's an overhead in the same sense that, you know, if you run a business, you have overhead, you pay employees, you pay, you know, whatever, space for buildings and so on. Those are all overheads. These are the overheads. The problem was, naively, people just expected they could plug in, just plug everything in directly. But if you do a preparation step, plug things in, let it evolve, and then clean it up after, there are ways to recycle things. So you basically, you have to erase stuff in an efficient way to prepare for the next. So when I'm talking about the overheads, I'm saying there are preparation and cleanup phases that occur in actual, as quantum computers get more and more structured, those steps would all be on a compiler level. We wouldn't think about them on the algorithm level, but on the compiler level, these will all be built in to clean up. So that was the idea. And then what I'm saying to you is that the concept of preparing and then cleaning up emerged out of the reversible computing way of thinking. We don't worry about it for Boolean type logic because we erase things, but when you get to reversible computing and quantum computing, you want to be very careful about erasing. So you have to get smart about that. This, by the way, this kind of thing, the compiler step, this is really not studied enough yet. And I can tell you, I have multiple jobs, and so I work in different places, and I'm working a lot with various people on developing quantum computers. And I can tell you that one of the big bottlenecks right now is exactly these compiler steps. That there are different places in the world that are putting a lot of work now into developing quantum computing, but the way to go from somebody writing a quantum algorithm to actually executing on a machine is very difficult. So you would have seen with Rigetti the PyQuil approach. Different companies are writing their own software, but right now everybody is scrambling trying to hire people who can know quantum mechanics and know compiling, and there's an extreme shortage of that. And so this is a big problem. There are actually companies that are really focused on that. Horizon in Singapore is an example. Joe Fitzsimons just started his company last year, growing like crazy because, and he's out looking for people who know compiling. So the things I'm telling you about this recycling are all really important right now because that's a bottleneck in the field. kind of get it. So just to be clear, you start up a company, you build a quantum computer. Somebody comes to you and says, okay, I want to test autonomous driving, machine learning on it. They have their software. How do they take their software and then somehow break out a module and have the module feed into the machine? And right now you need several people with PhDs to solve that kind of thing, and it's too expensive. Most companies are unable at this point. It's not the cost of buying time on a commercial quantum computer is not the barrier. The obstacle for them is being able to test their software components, being able to transfer that over into a commercial quantum computer. Okay, so now let's go back to the quantum computer and what it is. And so, as I said earlier, to me, a quantum computer accepts classical information as input. It yields classical information as output. Bits in, bits out. That's always the way I'm going to talk about it. I said earlier, and I'll repeat, that in the quantum simulation area, it's quantum in, quantum out. But to me, that's not yet in the form that we need to understand it as computation. Within the machine itself, then the classical information that goes in has to be converted to quantum information. So the computer has a step where it will write onto the quantum register, and it will then process it. So it does the logic. We saw the Boolean logic, and then reversible computing is permutation. And now it's this thing that we'll talk about in a moment, which is the processing that goes inside, and then it has to convert back to classical output. So it's classical information in, classical information out. The way we get classical information out is through measurement. So in the quantum computer, there might be measurements as it's processing, or it can save everything until the end and then perform measurement, and they're both equivalent. Okay, let's just say classical output is bits, so that after the measurement's done, then the measurement device has answers and they feed back. Now, what's going on inside the quantum computer is when we convert classical to quantum information, I'm just writing a quantum state in this way. And so for the quantum state, here's the quantum state. I'm just allowing B to be a string of quantum bits. So over here, we have an example. So imagine we have a string of some size, and the first bit is 0, and the second bit is 1, third bit is 0, and so on. The last couple of bits are 1. This we can understand as a classical bit string. But we put it inside of this ket, and I think you had a lot of lectures on quantum, so is everybody comfortable with what a ket is? Okay. So that ket is then representing the quantum register prepared in that state. But of course, in quantum mechanics, we can have a superposition of all such cases. So the string of bits can assume some value, it can assume a different value. We can prepare a superposition. The superposition has complex coefficients, and then they add up to form the full quantum state. And mathematically, these B's form a basis set for a Hilbert space. It's a complex Hilbert space, and these are vectors. So a Hilbert space is a vector space. It's complete, and it's got an inner product on it. And the fact that a Hilbert space has an inner product allows us to define an isometry. And isometries are maps. So every computer program is a mapping of it maps the state that's prepared in the machine to another state. And the mapping is always given by a unitary operator. And the unitary operator are the isometries. So the inner product doesn't change under unitary maps. So that unitary map is what changes this. Back to here, in a classical computer, every program is a Boolean function. Well, I shouldn't say that. Every computational problem can be recast as a decision problem. A decision problem is a Boolean function. And so we could think of all the programs we write as Boolean functions. In the reversible computing, every program is essentially a permutation map. So we could write it as permutation map. Now in quantum computing, every program is a unitary map. And a unitary map has permutations embedded in it. So every unitary map, if we're going to do classical computing, we can still do it on a quantum computer. So this is one of the key points, is that if we do classical computing on a quantum computer, we're simply writing the unitary maps, the unitary representations of those permutations. Here. Okay, so this is the nature and the set of all unitary maps is the set of all computations allowed on a computer. There's a subtlety there that unfortunately there's an uncountably infinite number of complex numbers. So there's a notion of reachability. So when I say all unitary maps, it's not exactly correct because we want some countable or finite number of maps for any computer. So there's a subtlety, but I don't think I need to go into that. Okay, any questions at this point? Sorry, in what logic? Boolean logic. Sorry, your question is not well posed. In the case of Boolean logic, would it be possible to say the problem is optimization? Is that what you said?
No. So in the case of quantum, would it be possible to optimize the circuit in the
Sorry, I'm lost again. In the case of quantum. So I will answer any question, but it has to be really well posed for me to understand. I have difficulty understanding any sentence that I can't parse. So, but I'm going to help you through it. In the case of quantum, you mean for quantum computing?
Yeah.
Okay, next step.
Would it be possible to optimize the circuit in terms of the number of gates?
Oh, I understand what you're asking. Okay, now I get it. Yeah, you're asking when you write it down. So a program is represented by a unitary map. And then what you're asking about is that unitary map has a cost. And the cost will be in terms of certain gates that I haven't specified yet. And then you're saying there would be different circuit possibilities. And they might be parallelized and all the rest. So absolutely, yeah. So your question is, could we take that unitary map and then optimize it? And the answer is yes. It's not efficient, just like in regular computing. But yeah, that's part of the compiler. So when I mentioned about the bottleneck in quantum computing now with compilers, one of the bottlenecks is the optimization. What does happen, what I've noticed, I don't work on that directly myself, but what I do notice in the literature is these optimizations are often done these days by people from this community. So in the reversible computing, one thing they developed was a lot of optimization techniques. And again, because of the easy embeddability of permutations into unitary maps, the optimization carries a lot of those techniques. So yeah, that's an important thing. It's actually very important, more important in classical computing. We don't worry so much because computers are so good. But right now in quantum computing, we don't have a lot of gates we can execute. And so that optimization is done diligently by all groups that I know. Okay, so this, I just put that cartoon up, Dilbert. So I'll read the cartoon to you just because I think it really picks up a key point. How's your quantum computer prototype coming along? Great. The project exists in a simultaneous state of being both totally successful and not even started. Can I observe it? That's a tricky question. But let's understand why he's saying it. This is Scott Diddams. He was a cartoonist, but he also seems to really understand quantum. He has some other ones. So the idea of being in a simultaneous state of being both totally successful. This idea of simultaneous, you'll see in the literature about quantum computing that it's often portrayed as going on in parallel universes or everything's happening at the same time. That refers to this superposition. But it's not really, these don't all exist as separate types of reality. They all coexist as a superposition like a wave. And then, can I observe it? That's a tricky question. That was the point of the measurement. So when we convert quantum information back to classical, and I said you measure it, it's a subtle point. You have to make sure you pick the right kind of measurements. So can I observe it? That's a tricky question. So the idea is that we have to perform the right kind of measurement that will yield the answer that we want. Uh-oh, is that blank? Oh, there it is. Okay, so here I'm just going to go through some sets of gates, and then I'll just show you an example of how to use it. And I know you've covered them before. Doesn't hurt, I think, to go through it a little bit. Okay, doesn't show up so well here, but this is the Hadamard Gate that you've already covered in these lectures. And so the Hadamard Gate takes the input of 0 and maps it to a superposition of 0 and 1 with a plus sign, and the square root of 2 is a normalization. So Hilbert space is an inner product space, therefore it has a norm. The norm of this state is 1. The root 2 is there to make sure the norm of the state's 1. And then the Hadamard takes the logical 1 and maps it to a superposition of 0 and 1. And the key difference is that's a plus sign and that's a minus sign. So that's what the Hadamard Gate does. It's got no classical equivalent because we don't have a classical meaning for talking about a superposition of 0 and 1. And then, and I'm sorry these aren't showing up very well here. Oh, they're looking. Yeah, it's fine on the computer. It's the projector's not carrying it. Okay, this is the C0 gate, but now the C0 gate, which I wrote over here, is not classical, but it's quantum. So going through the C0, the 0, if we had 0, nothing happens. If we have 1, nothing happens. But we could have a superposition of 0 and 1. So if a superposition of 0 and 1 comes in here, then it's a superposition of controlling that not operation. And this could be superposition. These could be entangled. And I'll show you the example to go through it. This is the phase shift gate. So it's hard to see. I'll write on the board. Again, I hope everybody can see what I'm writing. But we can do a phase shift gate. Phase shift gate takes, so if I do this dot here, and then I do, I'll call it the T gate. That's normally what we do now. Then it takes the state 0, maps under T to 0, and it takes the 1, maps under T to e to the I pi on 4, 1. That's the T gate. This is sometimes called the magic gate. So if you look in the literature, some people call that magic gate, and they talk about resource, magic resource, and so on. It turns out that in every implementation, one of those is hard to do. And so people sometimes call it magic. In cases where they think of these two as easy, that becomes the hard one. In optical implementations, these two are easy and that one's hard. But every implementation, there's challenges in doing both. The point of putting it in this row is that if you can make these 3 gates executed in your system. So if you're building a quantum computer, if you build a computer and you can make transistors, you can do everything. In a quantum computer, if you can make a Hadamard gate work, and you make a controlled NOT gate work, and you make the phase shift gate, preferably with the pi on 4, those 3 together are all you need to make a quantum computer. Most experimental efforts focus on making these 3, or some variant. They might not do a controlled NOT, they might do a square root of swap or a controlled phase shift or whatever, but this is the kind of thing they target. It's not the, okay, then when we make a circuit, we can count these gates. In the case of, there's another case of a universal set, and this one I put up because this relates to the reversible computing. So in this case, we have the Hadamard gate again that switches 0 to a superposition of 0, 1, 1 to a superposition of 0, 1, or we can take the Toefl gate. So remember I told you that in reversible computing, the Toefl gate's universal? Here, so I told you could have a Toefl gate or a Fredkin gate. Each one would be universal. We can make a reversible circuit using Toefl gates. So in this case, on a theoretical level, it's very nice that we can consider quantum computing reduced down to Toefl gates. And here just add in Hadamard gates. So we take our reversible computing, throw in these gates, and we have a set. So it's very nice. If you start doing, use the reversible computing literature, and again, I mentioned for compilers and all that, then you can add these in and easily connect the two areas. This I wrote because this is universal and this is universal. So I just wanted to give you an idea of the connection. So if we write a Toefl gate, and if that set is universal, then it means that we should be able to write everything here in terms of that and vice versa. And so the Toefl gate can be expressed in terms of the ones above. Here you can see the 3 qubits, quantum bits, and then this, the third one gets a Hadamard. The second and third have a controlled knot. Then there's a T dagger. So instead of pi and 4, it's minus pi and 4. Controlled knot, another T. Controlled knot, a T dagger. Controlled knot, a T and T dagger in parallel. Controlled knot, Hadamard, T dagger. Controlled knot, T. And an S is just a T squared. It's 2 T's. Okay, so this and this are universal, and this can be expressed in those so you can see the equivalence. So there's different ways. We could have other gates, but these are the most common ones that we look at. And then we deal with complexity. We could decompose in either way, write the circuit, and then calculate. Okay, any questions about that? All right, go on. Okay, so I'll just show you how to, I'm going to show you in the context of Schrodinger's cat. So I hope you've heard Schrodinger's cat. That's the famous case. Erwin Schrödinger, back when he did his interesting story. So Schrödinger, there was the formulation of quantum mechanics by Heisenberg, and then advanced by Born and Jordan, and it was all matrix mechanics. And then in the 1930s, Schrödinger came along and he used optics, so the behavior of light, as his way to think about quantum mechanics. So he didn't use matrices, he used a differential equation and used an optics way of thinking to formulate it. And when he part of it is he wanted to avoid the philosophical problem that Einstein saw, that Rosen, Podolsky, and Schrödinger, they were all bothered by. And that was the problem of what quantum mechanics implies. And so in Schrödinger's cat problem, he kind of shows that quantum mechanics makes even the concept of life and death not so well defined. So we think of life and death as, you know, if you have to pick a 0 and 1, 0 for alive and 1 for dead makes sense because we take being alive and dead as being absolutely meaningful states. And so in our modern quantum information way of thinking, we can imagine life and death in a superposition state. So I'll just go back here. If 0 is alive and 1 is dead, and it makes sense to apply a Hadamard, we can make a superposition of alive and dead. Schrödinger didn't think this way, but I'll cast it in that light. So here was Schrödinger's famous problem. Put a cat in a box, and the box is, you can't see in the box. So you can't see what's going on. So there's the cat, there's a poison gas, but the poison gas is only released if there's a nuclear decay. So here's the nucleus of a radioactive particle. And in alpha particle decay, it happens by a helium nucleus, so an alpha particle, bouncing around on the inside. And then when it escapes, that's what we call a radioactive decay. So you hold up a Geiger counter, and when it picks up that alpha particle, it goes click. And so you can detect a radioactive decay. The problem in quantum mechanics is it doesn't say the alpha particle's inside and then it's outside. It says that this alpha particle is in a superposition of being inside and outside, and it's really the detector, when it goes click, that makes it a reality that the decay occurred. So we like to think of radioactivity as going on, whether we see it or not, but quantum mechanics is not consistent with it. So in this case, when the nucleus gets out, the alpha particle gets out, then it triggers the poison gas and kills the cat. So what Schrödinger pointed out is that if quantum mechanics makes the non-decay or the decay not indeterminate, then the gas itself, whether it's released or not, is indeterminate, and therefore whether the cat is alive or dead is indeterminate. So let's just see how that works in terms of our gates. So I wrote a circuit down here. So this 0 represents an undecayed nucleus. This 0 represents a live cat. And then the Hadamard operation, the Hadamard gate, is waiting roughly a half-life. It's a half-life times log 2. And at that time, if you had a radioactive nucleus that was undecayed, after that time, then it will have a 50% probability of being decayed. So starting with a radioactive particle and waiting on the order of a half-life is equivalent to doing a Hadamard gate. Okay, then if the alpha particle goes, it causes the poison gas to release. That's the controlled knot operation, right? If no decay, don't do a knot operation. Well, the cat is alive. So a knot operation on the cat kills it. And so if there's no decay, don't kill the cat. If there is a decay, kill the cat. That's simply a controlled knot. So this quantum circuit with a Hadamard and a controlled knot represents the Schrodinger cat paradox. So I hope that gives you a feeling for what the Hadamard and C-naught do. And then down here, I just wrote it in terms of cats. So that's the 0, undecayed nucleus. 0 is the living cat. 1 is the decayed nucleus. 1 is the dead cat. And this is a 0, 0 plus 1, 1. That's an entangled state. So it's an entangled state. So it's not that the cat's alive or dead. It's simply entangled with the state of the nucleus. So that was Schrodinger. I'm not a philosopher. I'm just telling you Schrodinger's problem, and then I'm just showing you how to represent it in terms of that circuit. Okay, does that make sense?
If it decays, so it remain alive, unless it decays.
Well, and then the point is that even saying if it decayed or not, it didn't decay, I'm speaking in that logical way, but it never happens, right? In quantum mechanics, you can't take a quantum mechanical equation and say at this time it's decayed. So if it decayed, this is what would happen. If it didn't decay, this is what would happen. But by waiting a half-life times log 2, it's in a superposition of equal weighted superposition of this and this, and then that gas entangled it with the cat. Okay, so now that just gives you the basics, and then what the rest of this lecture and the other lectures will be about are the applications of quantum algorithms. And so here, I'll just put out, this, by the way, it's a free book I wrote. It's about 25 pages, costs nothing. Not worried if you read it or not, I don't get any commission. But it's how to build a quantum computer. I wrote that a couple of years ago. It's simply non-technical story about how to build a quantum computer. And then this part of the reason I'm giving this lecture is I'm thinking about writing a counterpart. A lot of people told me, they said, you know, I liked your book. I don't know if they really like it. They might just be polite. But how to build a quantum computer. But they say, I wish you'd write something about how to use a quantum computer at the same level. So this is what I keep thinking about, is how to write a counterpart to that, which would be about 25 pages, and then we do the algorithms. So in giving these lectures, part of what I'm thinking about is how to write something like that. And so in that case, the best resource I find at present, it's highly technical, but it's called the Quantum Algorithm Zoo. You can, I didn't put the reference, I didn't put the site, but if you just Google Quantum Algorithm Zoo, you'll find the site. And the Quantum Algorithm Zoo, you can see here, it says, this is a comprehensive catalog of quantum algorithms. If you notice any errors or omissions, please email me at steven.jordan@microsoft.com. Your help is appreciated and will be acknowledged. So it's a zoo, like you keep animals. And so every quantum algorithm that comes along, Stephen Jordan, who works at Microsoft, puts it into the zoo. He breaks it up into about 5 categories. So the first category are algebraic and number theoretic algorithms. He says what the algorithm does, in this case, factoring. He tells what the speed up is. So in this case, the speed up is super polynomial. And then he gives a description. When he does the description, gives references, and then he does do it. He acknowledges people's contributions. And so you can see in this case, it says, given an n-bit integer, find the prime factorization. It's kind of loosely worded. It's not as rigorous as I would like, but it makes it more readable. Quantum algorithm of Peter Shor, solves this in O tilde of n cubed time, gives the references. So it's a very nice place to go for, if you're interested in quantum algorithms and their application, you can just scroll through the quantum algorithm zoo. It's free to access, and you can see which algorithms fit. And more I'm doing this with my group. I've got a group of students, I call my applied quantum algorithm group, and we go through these, and then when people come to us and say, this is my software, it could be an automobile company, it could be whatever, but automobile, it could be facial recognition, whatever. They come along and they say, okay, this is what we do. Tell me how a quantum algorithm could help. And so our approach is to go through the quantum algorithm zoo, identify which algorithms fit which modules of their software, identify the requirements in their software. So where does one fit? And then what are the requirements in the software? And that's how we do it. So I'm just telling you our technique. In fact, this is being done by, there are companies, I mean, I do it for free, for grant money to pay students, but companies are setting up in that way. And that's essentially the method. And so this is what I'll be covering in my lectures, is the ideas of this quantum algorithm zoo. And I'm going to stay kind of, I mean, I get your feedback. I could go through and do algorithms. Like I've been told that you've already done the Deutsch-Jose and Grover search amplitude amplification. Or I can go through more high level and give you a sense of what the algorithms are and what their purpose is. Any feedback's welcome. If I do an algorithm, I could spend 3 lectures on Shor, or I could go through the high level. What do people, I don't know why you're here, so. You want Shor in detail? Oh, so you'd like me to go through Shor? Okay. That's easier for me. I've done that before. Okay, is that what people want? That I'll go through in this lecture, I'll just cover high level, and then I'll go through the details of the Shor algorithm. I'll ask Jibber. I'm giving them a choice at the moment, so you're walking at the right time. I'm just covering the quantum algorithm zoo, and then I was offering them the choice for the rest of my lectures, whether I would go through more high level. Do you know the quantum algorithm zoo? Have you been through it? Stephen Jordan, the quantum algorithm.
Okay.
You know this zoo? Okay, yeah. So I said that I could go through and discuss the algorithms and where they fit into applied problems, you know, and that was the machine learning, et cetera, but people seem to just want me to do Shor's algorithm, which I'm okay with as well.
I'd say go for the zoo, because Shor's algorithm, they didn't see any talk.
Well, that's why I asked. Yeah, I said it, but they, like maybe 5 people in the room talk and everybody else is silent. And then everybody who spoke said Shor, and I could do it. Other people can do Shor.
Anyone who wants to see Shor's algorithm, come take my class in the fall. And the zoo discussion I can't do in the fall, but Shor's algorithm I can do in the fall.
Yeah, okay. I mean, I think it's better value bringing me out to Karachi to do this. So yeah, okay. Is that okay then? I'll go through the high level. So Shor I could just do, you know, I've taught it so many times, it's easy for me to go through. Then this is harder work. Okay, then I'll go back to this. So then I'll go through the more high level. What I'll do is cover the quantum algorithm zoo, the different types, and where they can fit in. So I'll kind of give you a sense of these days where the value is in looking for quantum algorithms fitting in. Okay. And then just to round out on this lecture, the issue with quantum computing. So again, I'm trying to go through the issues also in the full architectural stack. So we have the high level, so just to put it through, we kind of have the bridge from the quantum algorithm zoo to building it. And so I just take a few more minutes to cover that gap. So in this case, we have the algorithm, we have the algorithms. In this case, we have to make the computer and they have to fit together. So there's an architectural stack where we go from the algorithm to the program and then down through compiler that optimizes, as you said before. But we also have to do error correction, fault tolerance, and work straight through to the physical implementation. So I'll just take a few minutes to mention that. And so here I just wanted to connect to the physics by telling you the classical realizations of a bit and quantum realizations of a qubit. And so to use the classical to try to get you to understand what the issues are with the quantum. So I just went through here and I just made a few notes about classical bits. Position of a gear or lever. If you go through, if you think about, people actually make Turing machine type systems now, where you have, thanks. So where you have a head going up and down to read, and gears that can move. And so these are mechanical bits. Really, the position of something encodes the bit. There's dynamic RAM. RAM is random access memory. This is charge buildup and a capacitor. So if you have charge buildup or not, that can be the 0 or 1. Read-only memory, ROM, would be presence or absence of a conducting pathway. When you do a barcode scan or a QR code, these are representing zeros and ones in terms of thin or thick black lines. So there are different ways to represent a bit. In the quantum world, we have different ways to represent a quantum bit. If we use a single electron, then it spins. So you can think of an electron with a spin. And if it spins one way, it causes a magnetic field to go up. Spins the other way, the magnetic field goes down. So whether the magnetic field goes up or down is a quantum bit. Flux quantum, this is done in superconducting systems. D-Wave computer uses a flux qubit. So their quantum computer is based on flux. IBM and Rigetti are not, they're based on charge. So the IBM and Rigetti quantum computers are based on the idea of whether a Cooper pair is 2 electrons, whether they're right or left of some junction. So it's interesting here. The D-Wave uses this, Rigetti, IBM, Alibaba all use that. You can have the energy as a dipole in an atom. So it's really, is the electron orbiting close to the nucleus or far? That can be the 0, 1. Light can be which way the light goes, polarization of the light, or what time it arrives. So there are different ways to do it. And somehow in our architectural stack, we have to be able to couple. This is all going in existing computers. So in the architectural stack, once we get below the compiler level, there has to be the physical implementation. All these things are considered by your computer. You don't see it, but it's all going on. Anybody here doing computer engineering? Yeah. Oh, one. So you know this, right? You learn. You go right down to the implementation level, right? Yeah. So one person here is doing it. This is actually very important. The computer engineers are able to take us all the way down the stack. This is what's going on in the quantum case. So I mentioned with the compiler bottleneck, this level of going all the way down the stack is tough. Microsoft is very dedicated to this. So in Microsoft, they have a large team and they're based in Redmond, and they are working all the way down. They have this language Q#. Do you guys know about this? So no, Q#, you know, yeah. So Q#, there's a object-oriented Haskell. So there's a F# is the Microsoft version of Haskell. Q# is built on F#, and they're doing it so that they work all the way down the stack. They work with experimental groups to get things to fit. So, okay, then when we do that, we have to make sure that we have our quantum error correction. Is that covered in these lectures or not? No. Okay, I won't go into it much. I'll just highlight to you in the high level again what goes on. So the idea with quantum error correction is that nothing works perfectly. And so I'll give you, I'll explain to you a little bit classically what goes on. Let's say that this room is very noisy. And then when I talk to you, we know I can represent everything in bits. So I could be giving this lecture instead of in English, I could just be doing it in binary. You know, just say 0, 1, 1, 0, 1, 0, 0, 1. You know, you'd listen, you'd convert back into whatever you wanted through that. So I could speak in that way. But if the room were noisy, you know, you might hear 0, 1, blah, 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 0. You'd miss some numbers, which would be terrible because you would be missing, you know, losing a bit could be important to understand the message. So the way that we get around that in engineering, information engineering, is that we encode. One way to encode is in blocks. So instead of saying, suppose my message to you is 0, 1, 0, but there's a small chance that a bit gets lost. So instead of saying 0, 1, 0, I just say everything 3 times. 0, 0, 0, 1, 1, 0, 0, 0, 0, 1, 1, 1, 0, 0, 0. And then if you hear 0, 0, you'll say, well, I heard 2 zeros and I didn't hear the last one. Or if you heard 0, 0, 1, you'd say there's a mistake. You do a majority vote. This is known as a repetition code. So the idea, if I say instead of 0, 1, 0, I say 0, 0, 0, 1, 1, 1, 0, 0, 0, is I'm doing a block code. I'm just making a block from the bit, putting it in a block, and then you decode. You hear 0, 0, 0. So in your brain, you convert that to a 0. Okay? So that's what block codes do. It turns out, and this was also discovered by Peter Shor. So Peter Shor 25 years ago did 2 great things, not just one. The Shor algorithm, and Peter Shor was also the one who formulated the first block code way of doing quantum error correction. This was important because I mentioned earlier Landauer objected that reversible and quantum computing would not be advantageous because there'd be an exponential overhead due to losses and decoherence. And Shor pointed out, just by taking classical information principles of coding theory, well known since the time of Shannon in the 1940s, he was, the idea by him and by others is that we can take what we know about coding theory and map it over to the quantum domain. And so in the quantum case, what we do is instead of taking 0, 0, 0, we would take the quantum state of 0, 0, 0, the quantum state of 0, then write it into 3 physical qubits to make a quantum state of 0, 0, 0, and then if an error occurs, we can correct it. On the other hand, there's more kinds of errors in the quantum world. So just like we have the, just go back here. So like 0 could flip to 1, that's a flip error. But here, if these were the qubits, you can have a sign flip. So you can have a flip or a sign flip. So in Shor's code, instead of encoding 1 qubit into 3, he encodes into 3 and then those 3 each into 3. That makes it 9. And so Shor code is 1 qubit into 9. But that's the idea. If we do that kind of coding, process there, then we can detect errors and decode. And that overcomes the exponential sensitivity to decoherence that Landauer was objecting to. So later, Landauer eventually accepted these ideas. He objected, very smart guy. His objections were really important and valid until these ideas came along. So we encode, it overcomes decoherence, then we decode to get the answer. There's another concept, fault tolerance. The big champion of this is one you read the most stuff. One who writes a lot about this is Daniel Gottesman at the Perimeter Institute. It's a very important point, and this is the idea of fault tolerance. So when you try to make things not be sensitive to decoherence and loss, you add things. You put more qubits in, more gates, more this, more that. Every time you add something new, you create new errors. So the concept of fault tolerance is that you have to design so that you are able to do quantum error correction and other things in a way that every time you add a new instrument, even though it brings new errors, it converges. The correction that you apply converges faster than the new errors expand. There's actually a theorem about this known as the quantum fault tolerance theorem or quantum threshold theorem that goes back to the 1990s. And so the idea is that it's an existential proof. The idea is that there exists some performance level, if everything meets it, then there will be convergence and quantum computing will be scalable. Okay, and that's it. Yeah, the quantum threshold theorem is where that lives. So that's the mathematical statement that we can overcome all these kinds of errors, assuming that the components are good enough. Basically, we build components in the lab, and if the component reaches a certain performance level, then it's guaranteed that the quantum computer is scalable. Okay, and now I'm going to finish this lecture by just sketching what the quantum computer could do. Okay, so I've put 2 columns here, quantum algorithms and quantum simulation. And the reason I put 2 columns is, to me, the quantum algorithms all fit nicely into the idea that a computer has classical input, classical output, quantum stuff going on. The quantum simulation is a little bit more complicated. It can have quantum input, quantum output. Let me go slowly through this slide to make sure you get the point. So quantum algorithms, two types that are important here. And this one, you've done the Grover search. You've learned already in this school. So the Grover search is underpinned by amplitude amplification. You've seen the technique. I think I put in a slide there, the concept of amplitude amplification. This one gives a quadratic speed up. The application is, the often discussed application of it is related to information security. So Shor's algorithm shows us that we can efficiently factorize and compromise security of RSA and other techniques for asymmetric key generation. But the other one is, once we generate key, we do things like AES. So we have encryption systems. So if we have a faster algorithm for search, some people argue that that could give us a way of not interfering the key distribution stage, but breaking encryption that uses key. I won't go into it. I don't think there's any stuff in this school about quantum encryption. No, it's related to quantum encryption. That's what the argument is. The interesting thing theoretically about it is it's a proven speed up. So as Gibran told me, reminded me to mention, all these complexity advantages are conjectured when I show you the complexity diagram. So that diagram back here. These separations are conjectured. They could all collapse. So once we get something like amplitude amplification, and it's a proven quadratic speedup, that's interesting. Quadratic speedup doesn't change one of those complexity classes, but the fact that it's a proven speedup becomes interesting, that it's not a conjecture that it's faster. It's provably better. The other famous quantum algorithm is the hidden abelian subgroup. This is what Shor's algorithm is underpinned by. So the hidden abelian subgroup problem, which I'll go into in my next lecture, this is the sub-exponential speedup. So basically, if we take factorization as an example, there's the limiting factor in factorizing numbers is the number sieve, which goes something like x. So if you're factorizing a number that's specified by n bits, then it's an exponent of something like the 1/3 power of n and the 2/3 power of n. So it's not quite exponential in n, it's exponential in roots of n. And the Shor's algorithm is polynomial, so that gives a sub-exponential speedup. And the hidden abelian subgroup fits with Shor's with factorization, discrete logarithm, Pell's equation, elliptic curves. Basically, every method we have today for public key distribution relies on the complexity of the hidden abelian subgroup problem. So it looks like a terribly mathematical term, but it underpins all forms of security for creating shared keys. So those are the two chief quantum algorithms from the old days. And then the quantum simulation, so it's 10:26, so I'll wrap up in a minute. So I think I'll stop on this slide. The quantum simulation, we take, this is a quantum state to a quantum state. So unlike the classical information, we have a mapping. I'll tell you, when I write down a Hamiltonian, since a lot of you are computer scientists, I'm going to tell you not as a physicist. So I'll write this down and then I'll stop. So remember what I told you, that in a quantum computer, then our program is a unitary map U. Okay? So that's the unitary map. That's the isometry map states. But there's something in mathematics. So in mathematics, we have a theorem. This is known as Stone's theorem. And Stone's theorem says for all u, there exists a self-adjoint matrix, well, self-adjoint operator H such that u is equal to e to the minus IH t. T is a real number, but in physics we think of this as being the time. H is that operator, and so it simply tells you that if you write a u, you can always write it as the exponential with some Hamiltonian h. Okay? And so to physicists, we often like to write this to describe the evolution, because this represents, this can be the representation of the equations of motion, how things change. So when I'm writing the Hamiltonian h, for the purposes of these lectures, I won't be a physicist and talk about h in that sense. I'll be more of a mathematician and just think of the Hamiltonian as a logarithm of that unitary map multiplied by the square root of -1. So this I is the square root of -1. And I think I'll stop at that. I'll pick up here when I start this afternoon. So thanks.